Hi, this is Mrs. Roble. For this video, we're talking about the structure of the atom, which is in Chapter 4. And this is probably one of my favorite chapters. Sometimes it's very challenging for students because we're talking about something that we can't see. It's kind of a black box. We haven't really been able to look at it effectively until the last 100 years or so. So looking at the atom is sometimes difficult for students because you don't have an electron microscope at your fingertips, so you can't necessarily get at the nitty-gritty of the atom. But you can see what the atoms do. If you look at this picture here, we're talking about lightning, and lightning is essentially the movement of electrons. And notice that lightning travels in a way to neutralize the charge, so it wants to go to the ground. And obviously it's very dangerous if you're not located in a safe place. One of the forefathers of atomic theory was John Dalton. He was an educator, he was a teacher. He's a very good thinker. He was able to reason out or tease some of the ideas about the atom. He saw atoms. Now, granted, he didn't actually look at atoms, but he assumed that these atoms were tiny hard spheres. And we're going to look at animation in a little bit to see whether or not that holds true. So he essentially thought that atoms must be hard spheres because he observed enough about matter that he came to that conclusion. Now, with his theory, he said that atoms of the same element are identical. That means all hydrogen atoms are the same, all oxygen atoms are the same, all carbon atoms are the same. There should be no variation within those. Now, when we look at the modern theory, we're going to see whether or not that holds true or not. He came to the conclusion through many years of study that different elements have to be different from each other. So there has to be a difference between hydrogen and oxygen and carbon. Otherwise, we wouldn't get the behavior that we have when we try to combine those atoms in many different ways. And this is groundbreaking because not everybody saw this, but Dalton said that they have to combine in unique ratios. So when water is formed, there has to be 2 hydrogen and 1 oxygen. When hydrogen peroxide is formed, there's got to be 2 hydrogen and 2 oxygen. So notice that he noticed that different compounds have different unique ratios, and that was groundbreaking. And then lastly, he said that atoms are the smallest bit you can get. So when you have a chemical process, those atoms cannot be divided up. That's the smallest building block that you have within chemical processes. Okay, so later on there were other scientists that also investigated the structure of the atom, and one of the more famous ones is J.J. Thomson. I love that name. He experimented with a cathode ray tube. Now, for your generation, you've been raised on flat screen TVs. Maybe some of you remember the older style computer screens where you actually have a fat body behind that computer screen. Cathode rays pretty much generated a lot of the television, a lot of the computer screens for a very long time. But because of liquid crystal technology, that pretty much has been removed. I will do a demonstration that shows you how cathode ray tubes operate. So J.J. proposed that because of this attraction to the positive plate, atoms contain negative particles. And these negative particles, he called them electrons. So he discovered actual presence of an electron, and he devised that there had to be some positive particles to compensate for that negative charge. If everything we touched was negatively charged, we would get a zap. And J.J. Thomson observed that that did not happen all the time. Now granted, in the wintertime, you may notice when you're walking on the carpet and you're dragging your feet that you can touch a friend and they'll get zapped. Okay, well that's a different situation. But overall, mostly everything is neutrally charged. Okay, so there was another scientist who came up with the plum pudding model. Now, you might say, why plum pudding? Well, that's what they knew. So plum pudding was a favorite dessert at the time, and they decided that atoms had to be very similar to what they know as plum pudding. So essentially what they're saying here is that these are electrons, the plums, and then the remaining portion of it is the positive charged part of the atom. So the question is this a good model? So the plum pudding model was put out there, but there were problems with it. It didn't accurately explain what was going on. So what happened is a man by the name of Rutherford made this really ingenious experiment, and this is something that you'll get to know very well. So he found a radioactive source. So he took some alpha particles and he essentially shot it through gold foil. So back in the day they were able to get a very thin thickness of gold foil. Now what he assumed is if it really was the plum pudding, he should get some ejection of particles back on the screen here. So here are deflected particles. And he should have got a whole bunch of them because the plum pudding was essentially a big atomic structure. However, he did not see that. So actually what he saw is on this side here, he saw a lot of alpha particles. So they were essentially captured by the screen that they put around the gold foil. Occasionally he would see a deflected particle. And what he did not know is these alpha particles came in contact with the nucleus and were deflected by the nucleus. So Rutherford's experiment was very, what's the word I'm thinking of? It was a revelation. So what happened was most of the alpha particles passed through, and it looked as though the atom was just empty space. But every once in a while there were a few that were deflected. So they actually came in contact with the nucleus, and they discovered that the nucleus is dense. So it's not just empty space. It's tiny, but it's very concentrated, and everything else around it is more empty space. So his conclusion was he discovered the nucleus. So they didn't realize that the plum pudding model was not an effective model because they didn't see electrons scattered throughout this positive sea. Instead, they saw a tiny dense nucleus that scattered these alpha particles. So Rutherford determined that the nucleus was very dense, and he determined that it had to have an overall positive charge because the alpha particles are positively charged, and two charges that are like each other repel, and that's where he got the deflection. And because of JJ, they knew that there were electrons, so they concluded with his experiment the electrons had to be outside of the nucleus. And that's where they got the idea of having these orbits that you see above. Okay, now I just have a couple more slides here. The next person that had some groundbreaking work with the atomic structure was essentially Moesley. So Moesley, he determined that there had to be a proton in the nucleus. So Rutherford found that the nucleus was positively charged and dense, but he didn't know that there was a separate particle within that nucleus. And Moesley had determined that there were protons within the nucleus. And he actually helped with the periodic table a lot. A lot of people, they hear about other scientists that created the periodic table. He's probably instrumental in creating what they call the atomic number. So he determined that each element had a specific number of protons, and those protons gave it an atomic number. The way he determined that is he looked at the X-ray spectrum of each element, and he noticed that these lines moved depending on how many atomic numbers you were looking at. So he was very instrumental in determining the presence of a proton within the nucleus. Okay, this is the last slide for this video. So Bohr probably was another scientist that was very instrumental in teasing out the structure of the atom. He used Moesley's information, he used Rutherford's information, and he essentially determined that because of Rutherford's experiment, the protons, which Moesley discovered, had to be in the nucleus, and he was trying to figure out where were the electrons. They knew they were outside, but where were they outside? And he decided that there had to be certain energy levels. So notice that above you see n equals 1, n equals 2, n equals 3. That looks very similar to the animation that I showed you earlier. So he determined as you increase the amount of energy for the electron, it must occupy a space outside of the nucleus further away. And notice that as you increase, the levels get closer. So they don't get just further away, they actually get closer further away. Okay, so be ready for a video assessment tomorrow.